Okay, let's get started. Today we want to talk about the singularity, or whatever it may be, at R equal Rs in the Schwarzschild metric. We have avoided this problem until now, so we always considered the situation that the star which we have at the center of our metric has a radius which is bigger than Rs, bigger than the Schwarzschild radius, which is the case for all known planets, all known stars. And then we don't have this singularity because the metric is valid only outside of the star. But today we want to discuss what happens if a star falls beyond this Schwarzschild radius, which theoretically should be a possibility. So we will now investigate what will happen if a star becomes smaller than the Schwarzschild radius, and this will lead us to the notion of a Schwarzschild black hole. So subject today is Schwarzschild black holes. So let me, just to remind ourselves, let me write the Schwarzschild metric again. It was minus 1 minus Rs over R. Okay, let me write it in detail. So I often write dt squared for this. dt tensor product with itself. No denominator, nonsense, but a c squared in front of it. Then I have plus the R tensor dr over 1 minus Rs divided by R. And then I have the angular part. So if I write it in detail, then this is sine squared theta d phi plus d theta. And because this is a fairly long expression, which will occur frequently in the following without ever being changed, I will introduce an abbreviation for this. Let me write GS, where the index S stands for sphere. So that's a standard metric on the two-dimensional sphere. We denote this GS. And we see there's a singularity. If R is equal to Rs, then we have a 0 in the denominator, which is always bad, right? And actually, when people realized that there is a 0 in the denominator, they started discussing this for decades. And it really took decades until they understood what's going on. So you may ask yourself, if I have a body which is smaller than Rs, so this value, R equal Rs, is disposed to an outside observer, so he could approach this value, then what will happen? Is it the end of the world if he approaches a singularity, or what will happen to him? So that's what we will discuss now. So, and actually what we will show, what will come out of the discussion, is that actually locally nothing bad happens. This singularity is just what is called a coordinate singularity. We can get rid of it by going to another coordinate system, and that's what we want to do now. So we observe that the metric coefficient GRR, so if I write this more fully than it is this here, this is this coefficient, yeah? The coefficient in front of dr tensor dr, that this thing becomes singular at R equal Rs. And we want to show that this is a coordinate singularity. That means that it can be transformed away. I've written it deliberately in this form. So here you see that this singularity could have two reasons, right? Either really the metric is bad. Yeah, something bad happens with the metric. Then we would be in trouble. Then it would be really something serious. Or this coordinate basis vector field could be bad. And this could just be a problem of the coordinates, right? So by going to another coordinate system, of course, I change the behavior of the basis vector fields. So if it is this thing which behaves badly, then we would have a coordinate singularity, and we can get rid of it. And that's actually what does happen. The metric is perfectly all right at R equal Rs. So we want to prove this. So we want to show that this is a coordinate singularity. So maybe one could guess already before starting doing any calculation that it might be not as bad as it looks. Because if you look, for instance, at the determinant of the metric, then this would be multiplied with this here. And you see the determinant is regular, right? This already gives you an indication that maybe it's not too bad. Another thing you could do is you could calculate curvature invariants, scalar invariants, which are formed out of the curvature tensor. They, of course, must take the same value in any coordinate system. If you find that a curvature scalar becomes infinite, then you can be sure that it's really a true singularity. You cannot get rid of it because it's infinite then in any coordinate system. But if you calculate curvature invariants at r equal rs, you will find that they are finite. And this gives you an indication, aha, maybe it isn't that bad. So let me write an indication. That's of course no proof that it must be regular, but it is at least an indication. Curvature invariants are finite at r equal rs. So for instance, you could calculate this thing, r mu nu sigma tau, and then transvect it with the same thing with upper indices. That's a scalar quantity, right? All indices are summed away. So that's a scalar, so it must take the same value in any coordinate system. So if we find that this evaluated at r equal rs becomes infinite, then we can be sure that it is a true singularity. But it is not infinite, it's perfectly regular. If you calculate this, I don't do this on the board, this would take a while. It's not a matter of 2 or 3 lines. What you find is it is 12 rs squared over r to the 6. So this is of course regular at r equal rs, nothing bad happens. But there is something bad happening at r equals 0. Yeah, r equals 0 of course is also a problem because I have also this in the denominator. And r equals 0 is in fact a curvature singularity. You see it from this expression, right? R equals 0 is really bad. You cannot remove the singularity by means of a coordinate transformation. But r equal rs looks harmless. And in fact, it is harmless. So what we will do now is we will construct another coordinate system in which the metric is regular in the whole domain from r equals 0 to r equal infinity, with the point r equals 0 itself being excluded. There the metric is bad. So, and well, there's an idea behind this construction. You might look at the metric, how could I come to know which sort of coordinate transformation would remove the singularity, right? And there's a strategy, there's an idea behind this. And the idea is that you look at radial light-like geodesics. So you send light rays along a radial line, and you look how they behave. And the coordinate transformation is made in such a way that these radial light-like geodesics are mapped onto straight lines. And then you will see that they go smoothly through r equal rs in the new coordinates. That's the strategy. So we consider radial light-like curves. Actually, because of the symmetry, if they move in the radial direction along an r line, they must be geodesics. Yeah? This is obvious from the symmetry, because a geodesic, if I start it tangentially to a radial line, it must stay on the radial line because of the symmetry. It cannot deviate in any direction, because everything is rotationally symmetric, right? So so I write curves, but these curves are automatically geodesics. So what is this? A radial curve is, of course, a curve where, well, light-like, of course, means g mu nu, or let me write dx mu by ds, dx mu by ds 0. And radial means d theta by ds and d phi by ds is 0. So I insert this, so I get only the first 2 terms, right? So I get 1 minus rs over r c squared dt squared by ds squared with a minus sign, plus dr squared by ds squared multiplied with 1 minus rs over r, and this is supposed to be 0. Okay, that's the equation for a radial light-like curve. For a light ray which moves along the radial line. And, well, we can solve for the derivatives. So let me write maybe I should write it in this way. This is so that you don't confuse it with the second derivative, right? It's the first derivative squared. Maybe it's better to write it this way. So let me write all the derivatives on one side. So then I get dr by ds, ds by dt squared. And what do I have on the other side? On the other side, I have this here with this together squared. 1 minus rs over r squared and a c squared, right? So that's it. Here I can use, of course, the chain rule. So I get this here, and then I can take the square root, and I get this is plus or minus 1 minus rs over rc. Okay? So why do I get two solutions? One with a plus sign, one with a minus sign? Well, obviously, the light ray could go in the positive r direction, outgoing, or it could go in the negative r direction, ingoing. So plus is for outgoing. Yeah, there the r by dt is positive. So this is outgoing radial light, and minus is ingoing radial light. Well, this differential equation can be easily solved. So I get dt is plus or minus c, no, sorry, dr. Let me put the c on the other side. C dt. Then I have here dr over 1 minus rs over r. So just to make this easier calculable, we multiply numerator and denominator with r. Then I have this here, okay? And then in order to break this in a convenient way, let me add a 0 here. Let me write it in this way. That's still the same thing, okay? But now I get a 1 here. So this is, or let me write the plus minus sign to the other side. C dt is, I get a 1 here. So this is just dr. And here I get plus rs dr over r minus rs. Well, and now any fool could integrate this. I don't even need my Bronstein in order to integrate this. I can do it by heart. So this gives a t on the left-hand side, plus minus ct. Here I get an r if I integrate this. Rs is a constant. Well, and 1 over is the log, right? So I get 1 over r, log r minus rs. And then I get, of course, an integration constant. So that's the solution. That's the equation for ingoing and outgoing radial light. Well, I can write the constant of the integration constant in a convenient way, so that I get a nice quotient here. So I can call the integration constant whatever I like. So I suggest to write it in the following way. Let's write C as rs ln rs plus or minus ct naught. Let me check. Plus ct naught. Yeah. So I introduced a new arbitrary constant t naught, and then I could write my c in this way. And then the solution takes a nice form. I get plus minus ct is r plus rs. And here I get ln r minus rs divided by rs. So I get ln r over rs minus 1 plus c t naught. So that's the equation of motion for ingoing and outgoing light rays. Okay, if I integrate here this to get the log, of course I assume that r is bigger than rs, right? Because otherwise I couldn't write it in this way. This is only true if r is bigger than rs. So this holds for rs, smaller r, smaller infinity. But my metric is also nice for r smaller than rs. It is bad at r equal to rs. but it is nice for R bigger and smaller than Rs. So I can also integrate this differential equation in the domain R smaller than Rs. And then I get just the other sign under the log. That's the only thing. Yeah? If I look up this integral, 1 over, then I have to be careful. Is this positive or is this negative? So I have to write the argument of the log in the form that I get something positive. So I get for the other domain, I get the same thing. This is R plus Rs. And now under the log, I get the other sign, because in the inner domain, this here is negative. So I get 1 minus R over Rs and plus Ct naught. So this is for 0 smaller than R smaller Rs. So I've integrated my radial light-like geodesic equation in the whole domain with the exception of R equal Rs. There's a singularity. You see it also in this expression, right? If I insert R equal Rs, then I get a 0 under the log, and the log is badly behaved at the value 0. So let me try to plot this. This is a very famous plot which we get now, and a very instructive plot. So I plot Ct over R. So we have here this value Rs, where the metric becomes pathological. And then I can calculate, I can draw these lines in the RT diagram for the ingoing and for the outgoing light rays. Let me begin with the ingoing ones. That's the one with a negative sign. So they come from infinity and go asymptotically towards R equal Rs. So they have shape of this form. And the outgoing ones are just symmetric. Yeah? If I solve for Ct, I get the same expression just with the other sign. So they are just mirror symmetrical. So they come here and approach the value R equal Rs asymptotically from the other side. So of course I should draw them in this direction because it goes from the past to the future. Yeah? So these are the outgoing ones. Something like that. And you see here's a light cone. Here's a light cone. Yeah? So if you are an observer, if you have to move with subluminal velocity, then the allowed velocity vectors are the ones inside the light cone. So you have to stick to the interior of the light cone. Well, and we can also draw the world lines outside, in the inside region. And then we get something of this sort. And again, the mirror symmetrical for the outgoing ones. Let me draw it this way. And here, now the light cone is like this. Yeah? So this is an outgoing light ray. Well, actually, I'm only showing R and T. So they are the angular coordinates. Of course, I have such a radial light-like geodesic for any value of theta and phi. So any point in this diagram actually represents a whole sphere. Yeah? So what this here represents is a sphere which expands, which is outgoing at the speed of light. And what this here represents is an ingoing sphere, which becomes smaller at the speed of light. And what I have in the interior is something very funny. I have also two families, but in this case, both families go in the direction of decreasing R. So both of them become smaller. So in a sense, here it's clear what is the inside and what is the outside of a sphere, right? The direction in which it becomes bigger, of course, is the outside, and the other one is the inside. But here, in a sense, both sides of the sphere are inside, because in both directions it becomes negative. That's what Roger Penrose called a closed trapped surface, what is found here. A surface which, in both directions, so the one which you would like to call outward and the one you would like to call inward, in both directions, actually the radius shrinks in the course of time. Yeah? And you see, if you are an observer, then you cannot escape from this cone. So you have to go towards the value R equals 0. So that's where the true singularity, the true curvature singularity sits. So you see already a couple of features from this diagram. What you do not see from this diagram is if it is really possible to go through this sphere at R equal Rs. So at the moment, the two things are disconnected, right? I have a nicely behaved metric outside of R equal Rs. I have a nicely behaved metric between R equals 0 and Rs. But the two things are disconnected. They are not glued together at the moment. And we will do this now by introducing a coordinate transformation. And the idea behind the coordinate transformation is that we map the ingoing light rays onto straight lines. So we invent a coordinate transformation. We introduce a new time coordinate t prime, which is made in such a way that the ingoing light rays are mapped onto straight lines. So you see what this has to be done. So this is an ingoing light ray, and this is an ingoing light ray. And what we want to do is we want to map this onto a straight line. So the coordinate transformation, in a sense, must pull this down, yeah, which goes to infinity, and pull this up, and then sew the two things together. And that's actually what we will do now. And these coordinate systems, they are called Eddington-Finkelstein coordinates. They were introduced by Arthur Eddington. That's the person who headed the solar eclipse expedition in 1919, famous English astronomer and mathematician. He invented these coordinates in the 1920s already, but he didn't see that actually they could be used to remove the singularity at r equal s. This was not his purpose. His purpose in this very short paper was to compare Einstein's theory with an alternative gravitational theory, a theory by Whitehead, which was popular at this time in England, but which is completely forgotten now. So this paper is only of a historic interest. And the first person who used these coordinates really in order to show that the Schwarzschild metric is regular at r equal s, this was David Finkelstein. So he discovered these coordinates again much later, in the late 1950s. But I think it's really justified to call the coordinates Eddington-Finkelstein coordinates, because he was a person who really did something interesting with these coordinates. So we transform now. We transform from these coordinates, which are called Schwarzschild coordinates, traditionally. Although, strictly speaking, Schwarzschild didn't use these coordinates. He used similar coordinates, but slightly different one. But it's now common to call these Schwarzschild coordinates. That's the one we have used until now. So these are the coordinates, or let me begin with t. T are theta phi. And I will use the ingoing Eddington-Finkelstein coordinates. And they involve only a transformation of the time coordinate. The time coordinate becomes a new time coordinate t prime. The other three coordinates remain what they have been before. And they are defined in the following way. Well, we define the new time coordinate in such a way that it maps this equation for the minus sign, that's the ingoing light rays, that it maps this onto a straight line. So that the relation between t prime and r should become linear. So we have to kill this term, right? This is obviously nonlinear. So we introduce it by the following transformation. So you write ct prime is, what is the sign? Plus or minus? Plus. So this is ct, and then plus this term, which we want to kill, rs ln r over rs minus 1. So this is in the domain rs smaller r smaller infinity. We will then see what happens with the extension. We will actually see that the resulting coordinate system can be extended down to r equals 0. But we do the transformation only in the outer domain. So let's see what we get. Then the ingoing radial light rays are what? So I express t in terms of c prime, then I get ct prime. So this is now on the other side. So I do it for the minus sign. I'm talking about the ingoing light rays. So this is minus. So So I have this with a minus sign here. I take it to the other side, and I get on the right-hand side plus CT plus RS, ln, and so on. So I get on the right-hand side my on the right-hand side CT prime, exactly. And what do I have on the other side? I have R plus CT naught, or minus, no, minus R, right? Yes, minus R minus C. Or let me put the minus sign on the others, that's easier. Yeah, of course, that's easier. Because I have the minus sign on the left-hand side, then I see it immediately. So on the right-hand side, I just remain with R plus CT naught. Okay, so that's for the ingoing radial light rays. And the outgoing ones. Yeah, so these are now straight lines. In the RT prime diagram, this is the equation for a straight line. And the outgoing ones, here I get this term twice, because it now comes with a wrong sign. So now I have the upper sign, the plus sign. So I have CT prime is plus CT. So CT prime is plus CT, plus RS, and so on. So I have R plus 2, RS, ln, R minus RS plus CT naught. Is that true? Let me check. Yes, I think that's true. Yeah, that's this equation with a plus sign. And CT replaced by CT prime. Well, and this can be easily plotted. And we will calculate in a minute that the metric is indeed regular. Or let me do the calculation first, and I show you the diagram afterwards. So for doing the calculation, of course, now in the metric, which is still written here, in the metric, I want to replace dt by dt prime, right? And the goal is, and if I have done everything correctly, it will come out this way. The goal is to show that we have no longer expressions of this sort in the denominator, that the metric is everywhere regular. So I need the dt prime, of course. So I need, so I get C, oops, here's the transformation. dt prime C dt plus RS. And if I differentiate the log, I get this in the denominator, and this is multiplied with RS. So I get R minus RS in the denominator, dr. So that's the transformation. So I have C dt is C dt prime minus RS. dr, R minus RS. So I have to substitute for CDT this expression, and then to see what we get for the metric. Let me do this. So the metric becomes what? G is, here it is written. It's minus 1 minus RS times R. And now comes CDT tensor CDT. So this object multiplied with itself in the sense of the tensor product. So I get, oops, CDT prime minus RS dr over R minus RS multiplied with itself. CDT prime minus RS dr over R minus RS. So that's the first term. Well, and the other terms do not involve a time coordinate, so I can just copy them. So the other terms are dr tensor dr over 1 minus RS over R plus R squared and the metric on the sphere. So I have to multiply this out. So I forgot a minus sign, right? I forgot a minus sign here. So I first write the term where these two things are multiplied with each other. And then I get minus 1 minus RS over R, C squared dt prime dt prime. And I get mixed terms. So I get minus 1 minus RS over R. this multiplied with this, and then this multiplied with this. So in both cases, I get a minus sign. So the minus becomes plus. And then I have, what do I have? I have CRS over R minus RS, and then dt prime dr plus dr dt prime, okay? Then the term where these two factors are multiplied with each other, I have a minus sign in front, and then two further minus signs, so it remains with a minus sign. 1 minus RS over R, RS squared over R minus RS squared, times dr tensor dr. And the last terms remain what they were. Plus R squared GS. Okay, let me see. I think with the first term I cannot do anything, so I just write it as it was. The second term, that's very nice. You see the term cancels. So if I multiply this with R, I get CRRS, and then I get R minus RS, and in the denominator I also have R minus RS. And then dt prime dr plus dr dt prime. That's very good. So one term which was in the denominator and could become 0 cancels already. Yeah. What about the other one? So I write this onto a common denominator. So let me begin with this term. Then I have a plus in front of everything. So I have, if I multiply numerator and denominator with R, I have R over 1 minus RS. And okay, let me leave it in this way for a moment. And let me here multiply with R. So then I get R minus RS, RS squared over R minus RS squared. And the whole thing comes with dr tensor dr. And the last term, R squared GS. And you see, at least one factor here cancels. We still have a 0 in the denominator, but I hope I can get rid of them also. Just looking at this term, is this here correct? Or should the I think the R should in the denominator, right? I multiplied this with R, and to compensate for this, I need an R in the denominator. So I think this should be down, right? Yes, I think so. Okay, last line. When we have reached our goal, c squared dt prime dt prime. This is nice. No singularity in the denominator. Other than at r equals 0. Okay, we cannot do anything about this. And here I write this on a common denominator, R minus RS. So then I get R squared minus RS squared. Oh, by the way, I wrote this term here twice. This is nonsense, of course. Yeah, it's outside of the bracket. So if I multiply both numerator and denominator with R, I get here R squared minus RS squared. This is R minus RS, R plus RS, the R tensor dr, and lo and behold, also this term drops out, and everything is regular. So I have no longer zeros in the denominator. You see this? R can now run from r equals 0 to r equal infinity without encountering any singularity in the metric. So this is regular for 0 smaller than r smaller than infinity. No zeros in the denominator. So in Eddington-Finkelstein coordinates, the Schwarzschild metric becomes regular in the whole domain from r equals 0 to r equal infinity. And well, what's physically happening at r equal rs can be read from a diagram when we plot now these light rays. So what we have done here in the Schwarzschild coordinates, we can now do in the Eddington-Finkelstein coordinate. And now rs is included. So we now plot ct prime over r. Down there we have plotted c times t over r. Now ct prime. So we have r equal rs, where now the metric is regular, no singularity anymore. And what are the light rays doing? Well, the ingoing light rays, of course, are mapped onto straight lines. We have done it this way. So they come in this way from infinity and go to r equals 0. And they pass through r equal rs without something particular happening. What about the outgoing ones? The outgoing ones are given by this expression. So here we still have the singularity, where this just means that the outgoing ones still approach this surface r equal rs asymptotically. So they go in this way. Oops. Yeah. And again, I draw the light cones. That's the interior of the light cone. And now something very interesting happens if you look at r equal rs. Here, well, this surface, r equal rs, asymptotically becomes an integral curve of these outgoing light rays, right? They approach this from both sides. So this here itself must be a light ray. So the light cone here is this. So one side of the light cone is just the surface r equal rs. And now you see what happens at r equal rs. If you are inside, if you are on this side of the surface, then you have no chance to escape to the other side. You would have to move with superluminal velocity, right? You have to stay inside the light cone. So you have to go in the direction of decreasing r. If you are outside, you are free to move either in the direction of decreasing r or of increasing r. But inside, you can only move in the direction of decreasing r. So that's where Finkelstein used the word one-way membrane for this. So he said r equal rs is a one-way membrane. So you can cross it from one side to the other, but not from the other to the one. Yeah? You can only cross it from outside to inside, not from inside to outside, if you move with subluminal velocity. Yeah? Where the word which is nowadays more common is event horizon. So usually we call this an event horizon. That's a word which was actually introduced already before Finkelstein's paper by Wolfgang Rindler in a cosmological context. And that's that's a word which we nowadays use for this. So we say this is an event horizon for observers outside of this surface, meaning that from the interior region, no signal can reach an observer which is outside. Yeah, if I'm here, everything I can learn about is confined to the region outside of the surface. I cannot know anything what's happening inside. So this is a horizon for me. I cannot look beyond this. So this is what we call an event horizon. So what I've said now, let me write a few words about this. And everything what I've said can be read from this diagram, from this Eddington-Finkelstein diagram, which is very instructive. So if you want to understand what a black hole is, then draw this picture by yourself and think about it for hours. And then you can read everything you need to know about black holes from this diagram. Okay, so I said that this word event horizon is usually used for R equal RS. And for the whole thing, we use, of course, the word black hole. This word was introduced by John Wheeler in the 1960s. And well, the idea behind this word is, of course, that we cannot get any signal from the inside. Yeah? So whatever happens inside the horizon, in the region between R equals 0 and R equal RS, will never reach an observer outside. So an observer outside cannot see anything that's happening inside. That's why we speak of a black hole. Not even light, let alone any other signal, can escape from the inner region to the outside. And you read it just from the shape of the light cones as they are drawn there. So I hope that this picture can be deciphered. Of course, in the lecture notes I will distribute, I have nicer pictures where hopefully it can be seen in a clearer fashion what I mean. So the first observation was, R equal RS is called an event horizon. And what this means is the following. Observers outside cannot receive the signal from inside. So the whole space-time how do we write this? So what I mean is the space-time which we get by transforming from Schwarzschild coordinates to Eddington-Finkelstein coordinates and then considering the whole range of the coordinate from r equals 0 to r equal infinity. So the space-time constructed this way is called a Schwarzschild black hole. Another interesting thing we can read from this diagram is that whenever I've been foolish enough to cross this surface, so whenever I'm inside, I have no other chance than moving towards the singularity, yeah? Because I can never escape from these light cones. So whatever I do, I cannot prevent my final fate, which will end up in the singularity at r equals 0, which is a true singularity. So the curvature is infinite. This means there are tidal force which will tear me apart. Nothing of this sort happens here. The curvature is perfectly regular there. So if you pass through this surface, you will not feel anything bad. Locally, you don't see anything, and that's a dangerous thing, yeah? Because you only after you have crossed the surface, then you will realize that you are in trouble, yeah? That you can never escape. But here, at the moment when you cross it, you will not see anything. You will not realize anything. Here, you will be torn apart by the tidal forces. So we observe from the diagram that whenever I'm inside, I will end up in the singularity. I cannot escape from the singularity. And the question you may ask is, maybe I'm lucky and this will happen in an infinite amount of time. Maybe it will take an infinite time. Then it wouldn't be too bad, right? But actually the time is finite. You can calculate it. You will do this in the next worksheet. So any observer inside r equal rs will end up in the singularity at r equals 0 in a finite proper time. And actually there's a bound for this which can be calculated. You will do this in the next worksheet. You will end up in the singularity here it is. Delta tau, that's the proper time interval which you have to live. It's pi rs over 2c. So rs, remember, is proportional to the mass. Yeah. So the heavier the black hole, the longer you have to live. Yeah. So well, that's obvious. The heavier the black hole, the bigger the Schwarzschild radius, and of course the longer the time which is available for you if you are inside. But this is a finite value. Yeah. So you will end up at a finite time in the singularity. And you may ask, what is the best strategy if you want to survive? So you might think screaming and kicking and trying to get out of it would help maybe. No, just the opposite. So the best thing you could do is just doing nothing. Just let yourself fall freely. This is the longest curve. The more you kick around, the faster you will end up in the singularity. So the limit case is a free fall trajectory. That's the longest one. And that's what you will calculate in the next worksheet. So I think that's number 11, right? Let me write it in this way. So for once, I could really give a practical advice for your life in this lecture. So whenever you fall into a black hole, don't move. Yeah, stay quiet. That's the best thing to do. Yeah, what else can we read from the picture? Well, this happens for every material body, everything which has to move with subluminal velocity when it is inside the horizon. So of course we can think of a star which collapses, and when it has fallen through the horizon, if it has become smaller than r equal rs, then this tells us that it will collapse to a point singularity in a finite time. Because this bound, of course, also works for the volume elements on the surface of the star, right? The surface of the star cannot move with superluminal velocity. So it is restricted by this bound. So this tells us whatever has happening before, as soon as a star has fallen through its Schwarzschild horizon, if it has fallen below r equal rs, then it will collapse to a point in a finite time. Yeah? There's no other chance. Whatever the processes are which may go, which may happen inside the star, this plays no role. It's a general bound, a universal bound. And we may draw a little diagram of this and then discuss what can be actually seen if a star collapses. So in particular, a star that has fallen beyond its Schwarzschild radius will collapse to a point singularity according to these equations. Yeah, that's what the theory tells us. To a point singularity in finite time. And it is this bound. It also works for the volume elements at the surface of the star, right? Because they cannot move with superluminal velocity, pi rs over 2c. Let's draw a diagram of this situation. So that's what we call gravitational collapse, right? Gravitational collapse. So how would this look like? So we draw this in the Eddington-Finkelstein diagram. So we have Ct prime over r. There's no negative axis. at r equals 0, the space-time ends. So I have here r equal rs. Now I consider a star, which in the beginning has a radius which is bigger than rs. But then the energy production comes to an end. The star collapses. It falls through its event horizon. And then it must end up in a finite time in the singularity. So the surface of the star would do something like that. Yeah? So I remove this now, because here in this region, the vacuum vacuum Schwarzschild metric is not applicable. Yeah? For the interior of the star, we need something else. But the Schwarzschild metric is valid in the outside. And now we can discuss the question, what do I actually see if this happens to a star? So you might think, well, I see the star collapse, the radius becomes smaller and smaller, then it falls through the event horizon, and in the end I see it shrink to a point. But that's not what I see, because I cannot receive signals from inside of the horizon, right? So I can see the star only as long as it is outside of the horizon. So the moment when it actually passes through the horizon is invisible for an outside observer, and also everything which comes after this. So if I'm an observer here, somewhere far away from my star, so I receive light signals. I receive a light signal from here. These are these radially outgoing light rays. The light from here, from here, from here, and they go asymptotically to r equal rs, right? If I extend them, and you see, I will never reach this point. It goes asymptotically. It approaches asymptotically this point, but I will never see this. This event actually happen. This event when the star falls through the horizon. So I don't see the star collapse. I see it approach the horizon, approach the horizon, approach the horizon, and this never ends for me. So what you will also do in the next worksheet is you will calculate the redshift. You will calculate how these light signals are redshifted. And then you will find out that they are actually infinitely redshifted. So put this more precisely, the redshift goes to infinity as this point is approached. And this means in practical terms, because any receiver, your eyes or a photographic plate or whatever, any receiver has a finite range of frequencies which can be detected, right? So what will actually happen is that the redshift will push the light rays out of the observable spectrum. So the light will become redder, redder, redder. So while the body approaches the horizon, it will become redder, redder, redder. And at some point, it's gone outside of the frequency range, which can be detected by your apparatus, by your eyes or whatever you're using. Yeah? And then you will no longer see it. So actually, in practice, you will stop seeing it before it reaches this point, because it is, the redshift has become so big that you cannot no longer detect it. So the fact that this object fades away from your view is actually, it comes about from the redshift. It does not come about from the fact that that it would move inside the horizon. You can never see what happens inside the horizon. So let me write this. An outside observer sees a collapsing star asymptotically approaching the horizon. The redshift goes to infinity. And again, that's something you will do in the next worksheet. So you will never see a black hole actually form, right? Or let's say a singularity form. So here's a singularity, right? Here the star is regular. Yeah, it has not yet collapsed, so that's the regular center of the star. So the moment when we actually have a singularity, this moment can never be seen by an outside observer. So when we say there's a black hole at the center of our galaxy, so you have the imagination that right now, there at the center, there's a singularity, right? But you have to, be aware of the fact that it's absolutely not clear what right now means. If you really mean your time coordinate, the time coordinate of an asymptotic observer in the Schwarzschild spacetime, at this time coordinate, you will never see the the event when the singularity is formed. So if this black hole has been formed by gravitational collapse of an object, that's what we assume, that it came about in this form, then this part of the space-time can never be seen for an outside observer. Yeah? And, well, actually, nothing on the world line here is simultaneous with events here, in any sense of the word. So actually, what we would see is just the process of the collapse, and we would see the object infinitely redshifted. So if we could look into the central part of our galaxy, if we could see the black hole itself, actually we would see the body before it collapses. We wouldn't see the status where we have a black hole. We cannot see this. We can never see this, yeah? According to this Schwarzschild theory. So the statement that there is a static black hole at the center of our galaxy is actually a fairly problematic statement. If you start thinking about it, you see that maybe it's not the right way of phrasing it. Okay, yeah, I have already mentioned in the last sentence that we do believe that black holes exist, right? That's a fairly recent development, say over the last 20 years. Well, I'm old enough to remember times when I'm a relativist since many years, when we relativists talked to astrophysicists and we told them about black holes. Well, they usually were polite, but you could read in their eyes that they thought, well, this is absolute nonsense. Yeah, this has nothing to do with the nature. And this has completely changed over the last 20 years. So nowadays, very down-to-earth astronomers speak of black holes as if they would be the most natural things in the world. We really believe that they exist. And there are two sorts of black holes for which we have good evidence that they exist. So the one are the so-called solar mass black holes, approximately of the same mass as the Sun. So they are observed in terms of accretion disks. So what we see, of course, we cannot see the black hole. We will never see a black hole. What we see is the X-rays coming from the accretion disk. So that's the first class. And the other class are the supermassive black holes, which we believe that they sit in more or less all galaxies at the center, in particular at the center of our galaxy. And we have very good evidence over the last years for this. So let me write this as the next statement. So there's good evidence, let me put it this way. That black holes do exist. So the first are solar mass black holes or stellar black holes. So m is the order of magnitude. So don't bother about a factor 5 or maybe even 10. So it's approximately the mass of the Sun. Yeah? Order of magnitude. I'm just talking about powers of 10. So they are observable by X-rays from accretion disks. So what we actually see is that there's an X-ray source, a source which emits X-rays. And from the physical properties of these X-rays, we deduce something about the mass and the other physical properties of the object at the center. And there are some indications that several of these X-ray sources are black holes. X-rays from accretion disks. And the most famous one of these X-ray sources, where people since quite a while are fairly convinced that it is a black hole, is Cygnus X1. Yeah, Cygnus, that's a constellation which in German is called Schwan. And X1, well, X stands for X-ray, and 1 was the first X-ray source which was found in this constellation. And the second type, maybe even more interesting, these are the so-called supermassive black holes. So here typically the mass is of the order of 10 to the 6 solar masses, or even more. So for the black hole at the center of our galaxy, one assumes that that's the order of magnitude of this mass. And they are observable with infrared cameras. By motion of stars. So what you observe what you observe are stars which move around the center of our galaxy. Well, you need an infrared camera because with an ordinary telescope in the optical range, you couldn't look into the region very close to the center of our galaxy because there's a lot of dust. Yeah? And this dust covers optical sources, all sources for optical telescopes completely. So you need an infrared camera with a high resolution. And these things were only invented in the 1990s. So one of the first of these high-tech infrared cameras was introduced in München by Reinhard Genzel and his group, and he was one of the leading persons who investigated the neighborhood of the center of our galaxies, beginning in the early 1990s. And he observed stars with his infrared cameras circling the center of our galaxies. And from the motion of the stars, he could deduce the mass of the object at the center. And on the other side, you knew from the angular diameter, you could estimate the range, actually, which is available for this object. And it came out that it must be very, very compact. So very high mass in a small range of space. And well, the most probable explanation is that it is a black hole. It's not completely proven by now. There are also alternative theories. Could be, for instance, a boson star, just for those of you who have heard about this. But evidence goes strongly in the direction that it is a black hole. So we are now fairly convinced that at the center of our galaxy there's a black hole. And since our galaxy is nothing particular, it's a very, very ordinary, very common galaxy. So this would be a good indication that also many other galaxies have a black hole at the center. So that's present status of the situation. So that's what we find from the Schwarzschild metric. So the Schwarzschild metric actually, I should say something. The question is, of course, is what we have done here. This is a good mathematical model for these black holes. And well, one of our assumptions was that the thing is spherically symmetric, which means that it is non-rotating. And actually, that's a matter of debate. If it's really a good approximation for these things to assume that they can be approximated as non-rotating. So in particular for the black hole at the center of our galaxy, some evidence points into the direction that it is fairly fast rotating. And then this model wouldn't work. We would need a modified model, which is called the Kerr metric. The Schwarzschild metric would not work for this. We would need the so-called Kerr metric, which is too complicated for being treated in this lecture here. But, well, at least some qualitative features, I think, are properly covered by this Schwarzschild model of the black hole, by this model of a non-rotating black hole. So, well, the properties that there's a horizon, that you cannot see the object falling through the horizon, and that you have this infinite redshift property, all this would also remain true if we had a rapidly rotating object. But the technical details, the mathematical details would be different. So this was a black hole. Now you might ask, well, we have done this construction with the ingoing radial light rays, right? This was the starting point which allowed us to draw this picture and to discuss this extension of the Schwarzschild metric into the region r smaller than rs. I could do the same thing with the outgoing ones, right? The theory is completely symmetric until here. So there are ingoing radial light rays and outgoing radial light rays. Now we had maps the ingoing ones onto straight lines. And then, of course, we spoiled the symmetry, right? This is no longer symmetric between future and past. This was, I have erased it, the older picture where I had CT over R. This was symmetric. If you reflect it, then it looked exactly the same thing. This doesn't, because we preferred the ingoing ones over the outgoing ones. So you could construct an analogous thing with the outgoing light rays. It would just be the mirror image of this, where you flip the time axis. And well, what you get then is not a black hole, it is what is called a white hole. It's just the time reversal of a black hole. And maybe I should briefly mention this. But at present, most people think that white holes are just a mathematical construction, that they don't exist in nature. So the black holes, there's fairly good evidence that they do exist in nature. White holes probably not. But as a mathematical construction, I think I should mention them. Let me leave the equation for the light rays. So a black hole has a horizon which can be crossed only from the outside to the inside. A white hole has a horizon which can only be crossed from the inside to the outside. So everything has to go out. Okay. So the analogous construction with outgoing Eddington-Finkelstein coordinates gives what is called a white hole. Now, what's this? So we do exactly the same thing, just with interchanging the ingoing and the outgoing light rays. So I have C, well, that's now a new coordinate, yeah, because it's now made in a way that it maps the outgoing radial light rays onto straight lines. So I call this T double prime. I have an R axis here. That's the horizon here. And now the outgoing ones are straight lines. So the ingoing ones are now asymptotic in this way. Okay? So you see the light cone is now in this way. So you see you can cross the horizon at r equal rs only from the inside to the outside. So an observer inside will never receive a signal from somebody outside. Yeah? And light can only go from inside to the outside, but not the other way around. So here the light cones are in this way. So that's a mathematical construction. It is just a mirror image of this picture. Yeah, just the time axis flipped, yeah, it's a time reverse situation of a black hole. And as I said already, up to now there's no indication that white holes actually exist. But well, a couple of years ago, many people were of the opinion that black holes don't exist, yeah, that they are just a mathematical construction, and now they are quite commonplace in astronomy. So maybe also the white hole, the concept of a white hole will become astronomically relevant sometime in the future. And the last remark I want to make about black holes, oh, by the way, I should mention that this person, David Finkelstein, he is still alive. Yeah, he's a fairly old gentleman now. I met him quite recently at a conference. He's a funny person. I remember he once was, when a new institute was founded in Clausthal in the Harz Mountains, he gave the, as a special guest, he gave the speech, which was at a very formal occasion. So a pianist played Chopin, and there were flowers all around. It was a very decent celebration. And David Finkelstein gave the main speech, and he appeared in a pink jogging suit with a hood. Yeah? And he gave the speech in this way. So this was a little bit unusual. So he really stick out from this crowd. But the speech was very good. The speech was very good. And I met him a couple of months ago in Jerusalem, and there we had what we call a Pudelmütze in German. During the talk, he had the Pudelmütze on his head. So he's a quite somewhat eccentric person, but very friendly and still quite in good health. I think he must be 85 or something like that now. Eddington, of course, is long gone. I think he died in the 1940s or so. Okay, the last remark I want to make about Schwarzschild and these extensions is the following. So we have now this first extension, the black hole extension, which was done with the ingoing Eddington-Finkelstein coordinates, and the outgoing one. You might ask, well, what is the maximal extension? Maybe can I do both things simultaneously? Can I glue a white hole to a black hole and maybe do something else in addition. So what is the maximal analytic extension of the Schwarzschild spacetime? And that was a question which was almost simultaneously with Finkelstein was solved in the late 1950s. It was done by several people simultaneously, most notably by Martin Kruskal and by George Sekeres. And the coordinates which do this, which gives the maximal extension, are called Kruskal-Sekeres coordinates. I want to make a brief remark about this. Indicate where the general idea nowadays is that this maximal extension has no physical application. That this whole thing, this whole maximally extended thing does not exist in nature. It involves a black hole, a white hole, and two exterior regions. But as a mathematical construction, I should mention is, so the maximal analytic so maximal means this is really, you really go as far as you can go. So you cannot glue anything at any end on this one. This is really maximal of the Schwarzschild spacetime. Schwarzschild spacetime was found independently by Martin Kruskal and George Sekeres in the late 1950s, practically simultaneously with Finkelstein's work. And it's done in the following way. One transforms from Schwarzschild coordinates so these were the coordinates we started out from, TR theta phi, to what is called Kruskal-Sekeres coordinates. They are denoted u, v, and theta phi. So the angular part is unchanged, but the time and the radius coordinate are made into two u coordinates, which will actually turn out to be light-like. So the u and the v lines are light-like, and I write the transformation for you. So they are defined in the following way. So if I give u and v in terms of t and r, then this can be done explicitly. The other way around requires solving a transcendental equation, which cannot be done in elementary fashion. So u is square root of r over rs minus 1, e to the r over 2rs cos ct over 2rs, and v is the same thing with a cos replaced by a sinh. So it's the same square root, the same exponential function, and then sinh ct over 2rs. When you try to solve this for r and t, you see that you cannot do so, because you have the r once under the argument of the exponential function and once under the square root. So you cannot solve this for r. Yeah? In terms of elementary function. Of course, it is invertible. It is a one-to-one coordinate transformation, but you cannot solve it for in terms of elementary function. And that's the reason why when you write the metric in the coordinates u, v, theta, and phi, you will still have expressions which involve r into the metric. So we would have to replace the r by u and v. So then the metric becomes the following. So our good old Schwarzschild metric, if you make this coordinate transformation, you find that it is 4rs squared, no, rs cubed, sorry, rs cubed over r, e to the minus r over rs, du tensor du, minus dv tensor dv, plus r squared and the metric on the sphere. So here you still have an R, where R is a function of u and v. Yeah, and it's a function which you get if you solve this for r and t, but this cannot be done in terms of elementary functions. So I cannot write this down explicitly. So that's the metric in these Kruskal coordinates. And now let's see what we get. So I plot v over u or u over v? V over u. And I will see that the domain on which this is regular is bounded by regions where r becomes 0, where I have singularities. And actually this region comes twice, namely on two hyperbolas. This is the hyperbola v squared minus u squared, or the other way around. V squared minus u squared, yes, is 1, and that's equivalent to r equals 0. So that's a singularity. Yeah, that's a singularity. And there the space-time ends. So the space-time is only on one side of it. And I have the same thing here. So this is also given by the equation v squared minus u squared is 1, or equivalently r equals 0. That's again a singularity. And light rays in this diagram, you can read it from this expression. So light rays means radial light rays, so there's no angular part. Light rays means that this must be 0. And then you see that these are just lines under 45 degrees. Yeah? So it's du squared minus dv squared is 0. And that's the equation of the lines under 45 degrees. So the ingoing and outgoing light rays are just the lines under 45 degrees. And this shows that if you come from the past, from this singularity and go to this singularity, then, well, you have two regions, two exterior regions. So let's call this 1, which corresponds to the domain r bigger than rs in this diagram. And you have another exterior region here on this side. So another copy of this. This is 4, or how do I want to label? No, 1 prime. And then you have these here. These are the interior regions. So here you have r equal rs, r equal rs, r equal rs, r equal rs. And you see that your light rays can cross this horizon only in this direction. So this is a white hole. Yeah? This is a white hole. White hole. This is region 2 prime. And here, oops, light rays can cross only from this side to this side, and other signals also. So here you have a black hole. Region 2. So this here is a region. Here's a black hole and the exterior region. That's the region which was covered by the ingoing Eddington-Finkelstein coordinates. This here was the region covered by the outgoing Eddington-Finkelstein coordinates. And you can glue the two things together along such a horizon, and then you get this complete picture. So it has two exterior regions. So you go here to r equal infinity, and you go also here to r equal infinity. Yeah, so you have two asymptotic exterior regions, and they lie to the future of a white hole region and to the past of a black hole region. So as I said, if something of this sort exists in nature, such a combination of two exterior regions, a black hole and a white hole, nobody knows. Well, the general impression is that it's probably just a mathematical construction which does not reflect something which exists in nature, but who knows? So what we believe that it does in nature is that it does exist in nature is something of this sort, yeah? Where you have a collapsing star. I had this picture where I had also the collapsing star surface drawn into the diagram, and then outside this ingoing Eddington-Finkelstein coordinates. That's what is very likely to exist in nature. So that's a black hole space-time, which results from gravitational collapse. These mathematical constructions, the white hole and this maximal extension, are probably just mathematical construction. constructions, but nobody knows for sure. Okay, so yeah, time is almost up. So that's what I wanted to tell about Schwarzschild black holes. I will continue this a little bit on Thursday, when I speak on the interior Schwarzschild solution. So I will mainly concentrate on regular stars, on the model for a star. Okay, so I will concentrate on static stars, but I will also make a few remarks about the collapsing dust bowl. This was a famous Oppenheimer-Snyder collapse. And then we will come back a little bit to this situation where you have a ball which collapses through its horizon and what an outside observer can actually see. So this can, for a dust ball, this can be calculated explicitly. And I will at least sketch a little bit the calculation. So we will not leave the subject of black holes completely. I will make a few additional remarks next time. And then in the remaining 3 lectures, I will talk about gravitational waves. Yeah? Then we have one Friday, then Thursday, and the very last Friday. In these 3 lectures, I will talk about gravitational waves. So that's the program for the rest of this term. Okay, thanks for listening.